Hey, this is Miss Miller, and I'm going to go over worksheet 3 today for net force particle model. And this worksheet basically uses all of the kinematic equations that we have looked at dealing with acceleration. So by definition, acceleration is a change in velocity divided by time, and there are 3 kinematic equations that we look at when dealing with acceleration, and those are listed up here. These 3 equations, they have acceleration in each one. That's why these are the constant acceleration equations. And then here we're starting to look at dynamics and Newton's second law, which also has acceleration in it. So for these word problems, we're going to have to use either dynamics or kinematics to find acceleration and then go across to another equation to find whatever we're solving for. But the key variable in all of these equations is acceleration. That's what sort of connects everything together. So we're going to go through and work, I think, about 4 problems. Looking at number 1 here. A race car has a mass of 710 kilograms. It starts from rest and travels 40 meters in 3 seconds. That's a lot of important information all at once. I'm going to go ahead and label that information. So mass is labeled with an M. That's going to be 710 kilograms. If it were in grams, I would have to change that. Starts from rest. So when you see the word from or to, which we don't have a to, so I don't know what a final speed is, but that from rest means that my starting velocity or speed is going to be 0 meters per second. And then we have 40 meters. If you're ever unsure of what a number represents, just look at the units. Meters are units for displacement. So that must be my delta x, 40 meters. And then 3 seconds. Well, seconds represents time, so t must be 3 seconds. Now the only variables I'm worried about are VI, VF, delta x, t, mass, and acceleration. So if I were to continue this table or list, I don't know acceleration and I don't know final velocity. I don't know what the problem is going to ask me for. Well, I guess technically I don't know my net force either, but we'll see what we're trying to solve here in a second. The car is uniformly accelerated. Okay, that's good. All that does is tell me that I can use those equations. If it wasn't a constant acceleration, then you wouldn't be able to use those equations. How big is the net force acting on the car? Okay, it's asking me to find F net. I know that net force equals mass times acceleration. That's what Newton's second law says. So I have my mass. I need to see or I need to try to find my acceleration. So, can I use information given to find acceleration? I have VI, delta x, and t. Well, if I look at my equations, here I have a list of the 3 equations just for easy reference. But if I look at those equations, which one will help me find acceleration? So, and I'm going to start with this one, and I'm just going to go through a process. Do I have my final speed? No, it's not listed, so I cannot use that equation. Let's see if I can use this equation to find acceleration. In order to find acceleration, I need delta x, t, and vi. And I have all of that information, delta x, t, and vi. So that's the equation we're going to use to find acceleration. Delta x equals 1/2 at squared plus vit. VI is your initial speed, so delta x, 40 equals 1/2 a times 3 squared plus 0 times 3. Now, generally, if you start from rest, we know that's going to go away. And the reason we know that is 0 times anything is 0. Don't make the algebra mistake of doing all of this and then adding 3, because 0 times 3 is not 3, but that's a mistake that I see often. So we have 1/2 times 3 squared. 3 squared is 9, so that's going to be 4.9a equals 40. So a equals 40 divided by 4.9, 8.16. That's meters per second. Oh, okay. So now I have acceleration. Can I find my net force? Yes. Don't make the mistake that I just about made and say, ooh, we're done with the problem, because we're not. The only reason we found acceleration was to find the net force, because that's what the problem was asking me for. So I'm going to say net force equals mass times acceleration. So 710 times 8.16. 710 times 8.16. That's, wow, that's 5,793.6 newtons. Depending on if your instructor wants you to use sig figs, I don't really fool around with sig figs. Sometimes I round, sometimes I don't. To me, it really doesn't matter. I guess if I was going to use sig figs, I would use 2 sig figs in my answer. So that would be, I think, 5,800 newtons. Okay. Number 2. Suppose that a 1,000-kilogram car is traveling at 25 meters per second. Its brakes can apply a force of 5,000 newtons. What is the minimum distance required for the car to stop? Let's figure out what I have. 1,000 kilograms, that's my mass. Speed may or may not be important. 25 meters per second. So if I come to a stop, that must be my initial speed. So its brakes can apply a force of 5,000 newtons. So I'm just going to write F equals 5,000. What's the minimum distance? So it's asking me to find a delta X car to stop. If it's going to come to a stop, that must mean that the final velocity is going to be 0. Now, dealing with these force problems, it's probably a good idea to draw a bit of a diagram. Let's say we have this normal force and force of gravity. Those are balanced because the car is not accelerating up or down. So when the car presses the brakes, we know it's going to slow down. So if the car was moving to the right, then the force from the brakes must be in a negative direction. Okay, so in this case, this is going to be my force from the brakes pushing against the motion of the car because it's going to slow it down. So based on my free body diagram, this should indicate to me that this force should probably be negative because it's pointing to the left. And just by sign convention, my class uses up as positive and right as positive. But you can really set your sign convention in whatever direction you choose. Here we are looking for stopping distance delta X. So if I look at my equations, in order to find delta X, now I'm not given time, so that means that I probably shouldn't try to use this equation or this equation because I'm not given time and I'm not given acceleration. But I do know my initial speed. And I do know my final speed because I'm coming to a stop. I can find my acceleration and then find delta X. So how am I going to find acceleration? Well, I know that Newton's second law says that the net force equals mass times acceleration, or acceleration is proportional to the force and inversely proportional to the mass. So I have my force, I have my mass. It's going to be no big deal for me to find acceleration. It's going to be negative 5,000, and my mass is 1,000. So my acceleration will be negative 5 meters per second per second. Okay, and again, that negative is just for direction. This indicates that I am slowing down to the right, or I'm slowing down in a positive direction. Therefore, my acceleration is negative. So now we can find delta X by using this equation. VF squared equals VI squared plus 2A delta X. So VF is 0. 0 squared is 0. VI is 25. So 25 squared plus 2 times A. I just found it, negative 5. That negative is important. If you have different signs, then you're going to get a different answer. And delta X is my unknown. So this is going to be, we're going to have 625 here, but we're going to take it to the other side. So negative 625 equals a negative 10 times delta X. So when I divide by 10, delta X is equal to negative, no, divide by negative 10. So delta x is going to be 62.5, and the units for displacement are meters. Sorry, I know that's hard to see. All right, number 3. A 65 kilogram person dives into the water from a 10-meter platform, and we're wanting to use forces here. So delta x, here's the water, here's the platform. What's going to happen is this person's going to start speeding up, and they're going to speed up with the acceleration due to gravity while they are in the air. Their acceleration will be negative 9.8 meters per second. Again, it's negative. I always use negative because I keep a constant sign convention of down as negative. My initial speed, I'm going to assume that if they're jumping, they started from 0. And it's going to hit, or this person is going to hit the water going at some speed. Now, once they get in the water is going to apply a force upward to actually slow them down. Again, so eventually down here, they'll come to a stop. So we have they're going to speed up to some speed, and then they're going to come to a stop again. So what is her speed as she enters the water? We can figure this out. That means that we're looking at this top portion. I know the displacement for this top portion is going to be negative 10. Why is it negative? Because we end up 10 meters below where we started, or we went down 10 meters. We moved 10 meters in a negative direction. There are 3 ways to say that there. So what's the speed? I do not have time, so if we look at our equations, this equation has time in it. That's not going to be helpful to find VF. This equation has time in it, and it doesn't even have VF in it, so that one's not useful. If I use this equation, then I can solve for VF. VF squared equals VI squared plus 2a delta x. My initial speed is 0. My acceleration is negative 9.8. Delta x is going to be negative 10. VF squared. So I'm going to do 2 times negative 9.8 times negative 10. So VF squared equals 196. Take the square root to get VF by itself. 14. I should have known that. 14 meters per second. Now, it's very important that we note that we have to ask ourselves, is that positive 14 or negative 14? Well, we're moving in a negative direction when we hit the water, so we need to put a negative there. Now, the reason we have to ask ourselves is because when we take the square root of something, it could be plus or minus. So it's our job to determine whether it is plus or minus based on our signs convention. Okay, so there's the answer to part A. Part B, she comes to a stop 2 meters below the surface. So it looks like right here, she continues to move for another 2 meters. So I'm going to label that as negative 2 meters. You can't see that. There we go, negative 2 meters. It's negative because she's still moving in a negative direction. Find the force on the swimmer by the water. So it might be, you might just want to find the net force, but that's not what we're looking for. If we think of the forces on this person while she's in the water, we're going to have the force of gravity. The force of gravity can be found by doing mass times 9.8. So that's going to be 65 because her mass was 65 kilograms. So 65 times 9.8 gives us 637 newtons. But there's also a force from the water. And this force of the water is not equal to the force of gravity, or else she wouldn't be accelerating. She wouldn't be slowing down. She would be descending at a constant speed. So we have an upward acceleration. And if I were to draw acceleration vectors here, then at every point we're going to have an upward acceleration coming from the net force of the water and the gravity. So we know that net force can be written as the up forces minus the down forces. So the force of the water minus the force of gravity. And that can be written as mass times acceleration. That's Newton's second law. So it's my job to find the force of the water. I know the mass. I know the force of gravity. I'm going to need acceleration in order to do this. So I'm going to work. All right. How am I going to find acceleration? Well, I know my initial speed when I hit the water is -14. What was the final speed in the first part becomes the initial speed for the second part. -14 meters per second. And then delta x is -2 meters. And VF is 0. I can find my acceleration. Guys, I can use the equation that I just used to find the acceleration again. And I'm going to do that right here. Sorry, I'm running out of room. So VF squared, I'm going to just plug and chug here. 0 squared, because VF is 0, equals VI squared, -14 squared, plus 2 times acceleration times delta x of -2. So this is 196. I'm just looking here. So -196 equals -4 times acceleration. So my acceleration is going to be a positive 49 meters per second. Now you say that's a pretty large acceleration. Well, think about the fact that the water is going to stop you really quick. Okay, so it's going to take a pretty large force, a pretty large acceleration to get you to change your motion that quick. That's why it hurts when you do like a belly flop or something, because you're experiencing a large force. Okie dokie. So I'm going to plug stuff in now. The force of the water, that's what I'm trying to find. I'll leave it as variables. Minus 637, I'm going to plug in the force of gravity, equals mass, my mass, 65, right here, times acceleration, that's 49. Okie dokie. So it looks like all I have to do to get the force of the water is add 637 to both sides. So 65 times 49 plus 637, 3,822, and the units for force are newtons. So there's part B. Alright, number 4. During a head-on collision, a passenger in the front seat of a car accelerates from this speed, so there's a VI, to rest. That means my VF is going to be 0 in 0.1 seconds. Seconds is a unit for time, so that's T. Calculate the acceleration. So this is straightforward. If you have VI, VF, and T, we use this equation. This is the definition of acceleration. Acceleration is the change in speed. We're going from 13 to 0. So my final speed is 0 minus 13.3, which is my initial speed, over time, which is 10.10 seconds. You get negative 133 meters per second. Now I might be like, okay, why is this negative? Well, again, we are stopping, and we're stopping very quickly, so we have a pretty high acceleration, and it's negative. Anytime you slow down, acceleration is going to be in the opposite direction at every point. So here are velocity vectors. There's some acceleration vectors. All right, part B. The driver of the car holds out his arm to keep his 25-kilogram child, who is not wearing a seatbelt. That's a problem. Make sure you're wearing a seatbelt. From smashing into the dashboard. How much force, this is a dark problem, must he exert on the child? Okay, so here's my kid. Not my kid. We have force gravity and a normal force, and those are going to be balanced. This dude is going to try his best to apply force in that direction to keep the kid from flying forward. So, what is that net force going to have to be in order to balance out this acceleration or counter the acceleration? Well, we know net force equals mass times acceleration. So we're going to have net force equals 25 kilograms times an acceleration of negative 133. 25 times 133 That is 3,325 newtons. That's a really large force, and that force needs to be negative because he's pushing back on the kid, and that negative is important. It's important that your numbers match your picture. This is a negative direction. This would be labeled like F. Alrighty. Now C. What is the weight of the child? Okay, weight is another name for the force of gravity, which is found by doing mass times 9.8. So 25 times 9.8, 245 newtons, okay? Convert the forces in parts B and C from newtons to pounds. 1 pound is 4.45 newtons. What are the chances the driver will be able to stop the child? Okay, so let's turn 245 newtons into pounds. There are 4.45 newtons in 1 pound. So 245 divided by 4.45, 55. So that's 55 pounds. The kid. Okay, that seems reasonable. Now let's look at the other force, 3,325 newtons. I want to divide that by 4.45 to get the pounds, because that is, then my answer will be 747 pounds. Let's put this into perspective. Some of the strongest people I know, and because I work with teenagers, I'm talking about like football players or something, they can bench press a lot. They can apply a lot of force. However, 750 pounds of force, that's a lot. And I don't think that any of them could really apply that amount of force. So chances that this dad is going to be able to save his kid, I don't know why it's a dad, the driver, I don't think they're going to be able to save the kid, because that's a lot of weight. It's a lot of force he's going to have to apply back on the kid. And even if he does save the kid, then that's going to hurt the kid. That's a lot of force being pushed on that kid. So it's not going to be good either way. So always wear your seatbelt. That was number 4. And 12. Oh, that was it. Okay. I hope that helps a little bit.